Okay, so now we want to look at what's the possible direction of the solution. What could they possibly do? Now, traditionally, the grid operators would address loads by building network, in effect, reinforcement, building new cables, new transformers, and so on. That's one approach. But let's just have a look at the size of the problem. So if we take here our balancing scales that we had before, and we take those green balls on the one side for the energy transition, what those figures were in 2021. These are figures from Germany. So if we say these are the installations of solar, of EV chargers and heat pumps. Now let's play forward into 2030 and see how those grow. So you can see already a large growth in solar panel installations. And we have to bear in mind that Germany has been quite at the forefront of solar power installations. So this is still some pretty strong growth. Heat pumps are set to grow as well. And again, in comparison to quite a few countries, Germany has been quite at the forefront. But the huge one here, we couldn't even fit it onto the slide, is how much EV charging is going to grow. And this is just in number of installations. This doesn't even take into account the size of the loads. The loads that are required for EV charging are really very, very big. So we have this one side of the balancing scales where we're going to be adding some extremely heavy weights. So what does the other side look like? If we took the investment in Germany alone into the distribution network alone, so not looking at the transmission level, in 2014, so before the energy transition really got going, we were spending about 3 billion euros a year. Let's wind that forward to today. That has already doubled to about 7 billion euros a year. Now let's play forward. What would be required to meet this demand in the future? You can see by the size of the circle, this is a huge jump to about 20 billion a year, not 20 billion one-off, 20 billion a year just to keep up. We really believe that this rate of growth, and it's not just us, it's other industry professionals, is just simply not possible on various different levels. We, as a society, can't afford to spend that much on our grids. We don't have the supply chain capacity to be able to deliver all of the hardware that's required that. We don't have the manpower to do all of that. All those factors, it's just too much growth too quickly to be able to manage it.
So you said reinforcement is not the solution. What is the solution?
Okay, so we believe the middle ground is smart grids. And to be honest, it's not just us who believe this. This is generally being put out there. We need to manage this transition through the use of smart grids.
And what do you mean? What is a smart grid?
Yeah. So for us, smart grids really are two factors. On the one side, they're self-aware, and on the other side, they're self-controlling. So by self-aware, we mean needing to deploy sensors out into the grid so that the networks know what's happening. And at the moment, you have to imagine at higher and medium voltage levels, there's a reasonable amount of transparency as to what energy flows are flowing. But then at the low voltage level, it's more or less a black box in most places in the world. And it's there where most of the energy transition is happening. And that's where we need to bring transparency. So we've got the self-aware side, but then we have the control side. Now, again, if we take the higher level voltage levels, you have a control system, you have people who can oversee that. And that's because the numbers there are so much easier to deal with. Just as a comparison, a typical relatively large network might have somewhere between 100 and 200 primary substations, whereas that same network on the low voltage level would have tens of thousands of secondary substations. You simply cannot manage that number of points and loads and the dynamic that comes with that through people sitting in a control room. You need a system which controls that. And that's where we mean that it is self-controlling. The system needs to be able to understand what's happening and be able to send control signals automatically to manage and balance the loads across the network. That is what a smart grid is.
Okay, perfect. So a self-aware and a self-controlling grid. But how does this smart grid helps DSO to balance this great dilemma you have showed?
Exactly. So on the one hand, it's going to help us achieve the energy transition, but it also has some advantages for the actual DSOs themselves. So the first level that we have is prioritization. So right at the moment, without knowing any information about the low voltage network, how does a DSO decide where and when to do what in terms of reinforcement work? And any smart grid solution should be able to provide to the DSO the overview and the information needed to know which transformers, which cables, which switching actions, which reinforcement works need to be done where and when, looking forward into the future. So to be able to prioritize the work to do the right things first. The next level is utilization. So we're all aware that in the network, you're not going to have an equal loading across all feeders and all substations. There's going to be differences. So there's going to be underutilization in some areas and high utilization in other areas. And so we brought this example here from one of our customers using our solution at the moment, where in the top right, you can see a situation on a feeder where the load was consistently beyond the fuse limit. So we have these little dots you can probably see on the slide at the top, showing where that fuse limit was being gone over. They were then able to make a switching action in their topology, which then moved that load through to another feeder. So this is a perfect situation. You've got existing infrastructure and you're able to use it better and therefore not have to invest. And so the more insights we can generate to enable utilization, the less money needs to be spent on networks. The next one is optimization. So in low voltage networks, the topic of neutral line loads is quite a big one. And this is caused by asymmetry in the phases. Now this can happen through a number of reasons, but something that's coming with the energy transition is EV charging. Whilst EV chargers quite often are installed across all three phases, they don't charge equally across those phases. And we see this again and again, that at the beginning of the charge process, maybe all three phases are being used, but then steadily as the charge process progresses, it switches over to one or two of the phases. And this causes quite big asymmetries. And if you multiply that out, so let's say all the EV chargers on a given street are installed in the same configuration, and everybody comes back at the same time and has the same situation, you can imagine the size of the neutral line loads. And there are other causes out there, but for the DSO to be able to identify where this is happening, build it into calculations, and also to possibly take actions to reduce those loads will create a much more efficient network. And then finally, we have strategize. So by being able to take the data that we're providing DSOs, they're able to then plan better for the future. With more accurate data, we're going to make better decisions. So we brought an example here from Düsseldorf, where they were wanting to deploy further heat pumps out into a particular area of their network. And they had their simulation tool, which had predicted where and to what extent they could roll out these heat pumps. And they then wanted to use our data to validate whether that simulation was correct. And the table in the top right that you can see here, the gray lines show where the simulation and the real world measurements that we were taking were quite accurate. However, you can see two feeders, number 4 and 7, were quite far out. So we had 50% in one direction and about 60% in the other direction. And so by being able to take that data, you're able to correct the models and make better decisions. I mean, imagine in this scenario, you'd underestimated what the load was, deployed the heat pumps, and then had to reinforce the network as a result. Would that have been the right decision? But with real world data, those decisions can be made much better.
Okay, perfect. Thank you very much for these impressive examples. So we discuss which approach SMIGHT has. So you said it's important to phase the energy transition very fast. What is a SMIGHT approach by bringing devices, equipment, data very fast in the grid?